Hi guys, it's Dr. Bay and here's Bugsy, and today we're going to go over part 3, the final part of pericyclic reactions, so stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
Retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly fly, give rise to the complexity of life, living on a dream across the 7 seas, learning about spectroscopy. Organic chemistry.
The last type of pericyclic reaction is a sigmatropic rearrangement, and just like the other two types, sigmatropic rearrangements are concerted, involve a ring of electrons moving around in a closed loop, and occur through a cyclic transition state structure. There are two types of sigmatropic rearrangements. The first one is a 3-3 sigmatropic rearrangement, where a sigma bond breaks and a new sigma bond forms between C3 and C3. And there are actually two specific 3-3 sigmatropic rearrangements that you'll learn about, called the Cope and the Claisen rearrangement. Another type is a 1-5 sigmatropic rearrangement where a CH bond breaks and a new CH bond forms. This is also called a 1-5 hydrogen shift or hydride shift, which can be seen in a carbocation rearrangement to form a more stable carbocation. The Cope rearrangement is a 3-3 sigmatropic rearrangement where all 6 atoms, part of the transition state structure, are made of carbon atoms. This equilibrium favors the right side because more substituted alkenes are more favorable and stable. In this following example, predict the product of the following reaction. First, we're going to draw an arrow from the C1-C1 sigma bond to form a new pi bond between C1 and C2. Then we'll draw another arrow from the C2-C3 pi bond to form a new sigma bond between C3 and C3. Then a C2-C3 pi bond moves over to form a new pi bond between C1 and C2. This forms a new cyclic molecule with 2 alkenes. The Claisen rearrangement is also a 3-3 sigmatropic rearrangement, but is the oxygen analog of a Cope. The arrows are super similar, but with an oxygen atom at the 1 position. The reason why this rearrangement occurs is because the left molecule is similar to an enol, where there is an oxygen atom connected to an alkene at the vinylic position. Recall that enols are unstable and tend to tautomerize into a more stable carbonyl. A Claisen rearrangement represents that tautomerization, where the new product is again a new, more stable carbonyl. In this example, predict the product of the following sigmatropic rearrangement. If you number wherever the oxygen atom is as number 1 and the alkene carbon it's connected to as number 2, this gives you a reference point to where exactly the enol in the molecule is. The alkene pi bond part of the enol always breaks to form the new pi bond connected to the oxygen atom. Then you can draw the other 2 atoms going in the same direction, which in this example is going counterclockwise. After drawing the arrows in a closed loop, you get the following product where there is now a new sigma bond between the C3 carbon atoms and a new ketone at C2. So in summary, sigmatropic rearrangements occur to form a more stable molecule, whether that be a more substituted alkene in a Cope rearrangement or a more stable carbonyl in a Claisen rearrangement. But both mechanisms are similar in the number of new sigma bonds being formed.